Okay? Now, who's this in the picture? Let's measure your geekness. I'm sorry?
Harrison Ford?
Harrison Ford it is not, but he would be honored to think that you think that of him.
Captain Kirk.
Captain Kirk. What's his full name?
Oh, it is.
James T. Kirk, and the T stands for?
Tiberius.
Oh, serious geeks here. Serious geeks. Tiberius. Very good. Okay. Now, Captain James Tiberius Kirk, William Shatner, is the key to understanding the concept of a field. We're going to build on the analogy with the gravitational force that we understand. You remember that Newton gave us this universal law of gravitation, which told us that any two masses that were separated by a distance r would experience a force given by this formula. Now, it turns out that this constant of proportionality here was incredibly difficult to measure. Imagine taking 1 kilogram and putting it 1 meter away from another 1 kilogram and measuring the force between them. That force would be the value of this constant. And of course, that's not the way Henry Cavendish did it. He had that great big dumbbell with massive granite balls at the end, and he found the force exerted by two large masses on each other by measuring how much it twisted a wire. I told you that story at 2:05. Very, very inspirational. It took 100 years to find that constant. Now, the important thing is that the force is equal on both objects. Even if one of those objects has a huge mass and the other one has a small mass. It shouldn't surprise us that Newton's third law is built right into Newton's law of gravitation. It's Newton. Okay? And if I look at the reason that the third law applies, or is valid, I've got m1 times m2. Let's say m1 is big, 1,000,000, and m2 is small, it's 2. Well, 1,000,000 times 2 is 2,000,000. If you want to know the force on the other object, switch them around. 2 times 1,000,000 is still 2,000,000. When you take the product, it doesn't matter which way you do it. 1 times 2 or 2 times 1. Now, we found last day that the electric force has exactly the same form. And by that I mean this 1 over r squared dependency. That means that just like the gravitational force, twice as far away is 1/4 as strong. 3 times as far away is 1/9 as strong. Now, in this case, it's not the masses that experience the force, it's the charges. And so instead of multiplying masses, I multiply charges in coulombs. And there's some very important differences between this case and the gravitational case. The first difference is that with mass, there's only one flavor. It's positive. And so it turns out that all gravitational forces are attractive. It turns out that we have 2 flavors of charge, and what we find is that when the charges have the same sign, if they're both positive or they're both negative, I get a repulsive force. If they're opposite sign, one positive and one negative, I get an attractive force. Now, the other big difference is that because we only had positive mass, we could use that formula for large objects like the Death Star. Indeed, that is exactly why Newton created the calculus, to prove that the pull by the Earth, all the little parts of the Earth on the apple, was exactly the same as if I put all of that mass of the Earth at the center of the Earth. Now, it turns out we don't get that result with the electric force. Because there's positive charge and negative charge, we have a complication. What does this formula give you if Q2 is 0? Gives me 0 force. And folks, that's not what we saw. That's not what we saw right here in River City. When I took that piece of wood, it had 0 charge. It was neutral. And yet I had an attraction to the rubber rod. I had an attraction to the glass rod. I had that great big piece of lumber. It was neutral, Q0. And yet I was able to pull it around in a circle with a rubber rod. The fact that I've got positive and negative charge that can cancel out and give me this Q equals 0 means that I have to be very careful with this formula. With gravity, I don't have to be careful because calculus shows me I don't. But with the electric force, I have to be very careful. I can only use this equation if my charges are small. Well, how small is small enough? If my charges are small compared to the distance between them. Now you remember, the reason a neutral object gets attracted to things is because we can set up a charge separation, where even though the can is neutral, has charge of 0, one side of the can is positive and the other side of the can is negative. Well, if that can is so teeny tiny that the one side of the can is about the same distance away as the other side of the can, it doesn't matter. It's only when the size of the object is large compared to the distance between the objects that you have to worry about this, this induced charge separation that we talked about last day. See if your neighbor understands this idea.
Charges are small compared to the distance. Which one is it? Wait, Greg, can you say it again? Is that right? Did I write it?
If the size of the Q's are small compared to R, yes.
The size of the Q?
The size, not the charge of the Q, but the size. Oh. Okay. Now, you had a problem 2, we didn't have to turn it in, but you had one charge that had 3 times as much charge as the other charge. And graphically, it looked like this. And if I have 3 charges there, I've got 9 charges there. And the question is, how did the forces that they exerted on each other compare? And if we believe Newton's third law, if we believe Coulomb's law, we recognize that these forces, this would be the electrical force by 1 on 2, this would be the electrical force by 2 on 1. This is going to be 2 on 1 is going to be K Q2 Q1 over R squared. This force by 1 on 2 is going to be K Q1 Q2 over R squared. Well, Q2 times Q1 is equal to Q1 times Q2. They have to be equal. And indeed, as we would do in 205, would put a tick mark there and a tick mark there indicating that they are a match set, part of the same interaction. They are third law companions. Okay? Now I want to warn you about this equation. I find that beginning students find that equation somehow fascinating, and they try to use it to solve every single problem. Now I've told you in the past about my sledgehammer. how that's my tool, and when I get to fix something around the house, I go and grab that sledgehammer. It's not the tool for everything, and this equation is only going to be useful when I have point charges that are far away from each other. Okay? Now, let's go back and talk about this picture. It's the only picture that I could find on the intertubes where it looked like Captain Kirk was being zapped by a force field. So let's talk about a force field. You remember in the original Captain Star Trek show, if you're old enough, they went to all these different planets and encountered these different cultures. Now, making up a new planet is expensive when, you know, even for Hollywood. You gotta build buildings, they didn't have the technology that we have today to make it with computers. So what they did instead is they just went to those planets and they said, oh, they don't have a good atmosphere. They must live underground. And once again, everyone was down in the caves. You know, just like last episode. It was cheap. Okay? Now, in every one of those episodes, we got Captain Kirk leading the charge, and as he's running through this cave, suddenly he hits a force field, he's thrown on his keister. Okay? Now, let me make 3 points about that field. First of all, that field is invisible. Captain Kirk can't see it, otherwise he wouldn't have gone into it. Second of all, Captain Kirk didn't make the field. That field was made by the Klingons when they were the bad guys before they became the good guys and joined the Federation. It's all complicated. Captain Kirk did not make the field. Okay? The third point, there is no force there in the cave until Captain Kirk is put into the field. Then he feels the force. The field puts a force on the Captain Kirk. 3 points that will be the key to understanding the electric field. It's invisible, Captain Kirk didn't make it, and there is no force until I put Captain Kirk there. Hold those thoughts. Now, going back to the gravitational field, in 205 we didn't call it that, but we sort of calculated it. We said that if we wanted to find the gravitational force on a book, all we had to do was take the mass of the book and multiply it by 9.8, let's call it 10, newtons for each kilogram. Folks, that 9.8 is the gravitational field strength. That is the gravitational field. Okay? Now, we can also calculate that same force with Newton's universal law of gravity. As long as we know the radius of the Earth, not hard to calculate. The mass of the Earth was very hard. That's what Cavendish gave us. But with those two numbers, we can plug into that formula the universal constant, the mass of the Earth, the distance between the center of the Earth and the book squared. And what we see is that all of that stuff in the box is the 9.8 newtons for each kilogram. And so this gravitational field strength was just a mathematical shortcut. I didn't want to plug in the mass of the Earth every time I calculated a weight force. I just did it once. I got 9.8 and then I used that forever after. Okay? That was the depth at which we went into the idea of a field in 205. Now, as long as you stay close to the planet's surface, the gravitational field is deadly boring. Everywhere in this room, it points down, and it has a magnitude of 9.8 newtons for each kilogram. If I were to visualize it, it would be a whole bunch of vectors, one vector for every point in the room, all pointing down, all the same length. That's boring. Now, if I'm willing to go a little bit further away from the planet, I mean here at the planet's surface, if I take 1 kilogram block it's going to feel 10 newtons. But if I go further away, a 1 kilogram block would feel, let's say, 5 newtons. Let's say I go far enough away that it feels 5 newtons. Now, folks, the next minute is going to be the key. This is where you understand, don't understand a field. What if I put 3 kilograms there? What's it going to feel? Remember, if I had 1 kilogram there, it felt 5 newtons. If I put 3 kilograms there, it feels 15 newtons. Okay? Now, folks, there are always 2 arrows that you have to keep straight. There's the red one and the blue one. The red one is the force. The actual force that actually acts on the actual mass that's right there. It's real. And then there's this blue vector, and it's invisible in your mind. And it has waffle words. Listen for them. This blue vector is the force that would act if I put 1 kilogram, 1 unit of mass there. It's the force that would act if I actually put 1 kilogram there. This one is imaginary. It exists there whether the 3 kilograms is there or not. When I put the 3 kilograms there, I get an honest-to-goodness force. Okay? Now, the gravitational field strength at that location, I would say, is 5 newtons for each kilogram. Now, what if I told you that a mass of 5 kilograms experiences a force of 35 newtons? What would the blue vector be? 7. It would be 7 newtons for each kilogram. And so the gravitational field of the Earth looks like this. There's nothing out here being pushed. But if I put something there, I could find the red vector, the push, by just taking the number of kilograms and multiplying it by 7 newtons for each kilogram. Okay? And so the formula that I use to find the red vector is that one right there. That formula says, this is how hard 1 unit of mass is going to be pushed. Multiply that by how many units you actually put there, and that will give you the actual push. I hope you're bored. I hope you're bored silly, because that's the perfect state to be in to make the next step. The next step. The electric field is defined exactly the same way. Only instead of pushing and pulling on masses, kilograms, it pushes and pulls on charges, coulombs, either an excess of electrons or an absence of electrons. Now, let's see if you can use the analogy. Let's say that this bottle of water is charged positively. I hope that's water and not tequila. And that this is charged negatively, and that's negative, and that's negative, and that's positive. Now, those charges are going to set up an electric field in this room. And unlike the gravitational field, which is boring, everywhere the same, the electric field, due to these sources, these Klingons, if you will, could be very, very different at different locations. Over here it could be pointing this way. Over here it could be pointing that way. Over here it could be strong. Over there it could be weak. And every point in this room would have a different arrow. Now let's see if we understand what those arrows mean. If I told you that the electric field right here, was 5 in that direction, and I'm leaving the units off on purpose. What does that number 5 tell you about this region of space, this location?
If there were something there.
What's that?
If there were something there, it would act on the object by 5. Something like that.
If, oh, the first word out of her mouth was a waffle word, and that's perfect. It's perfect because you always use waffle words when you talk about blue vectors. If I put something here, what something would that be? In the case of the gravitational field, we always put 1 unit of mass, 1 kilogram. What do we use for the electric force? Electric field. 1 unit of charge is 1 Coulomb. So, the 5 tells me how much force there would be in newtons if I reached into my pocket, heaven forbid, and pulled out 1 Coulomb of charge and put it there. That positive 1 Coulomb of charge would feel a force of 5 newtons in that direction. Well, what if instead I pulled out 2 newtons? What would it feel? 10 newtons. What if I pulled out 3 coulombs? 15. Folks, this idea of a field is very, very much like a rate. Okay? Let me just define it first. The electric field is the force that plus 1 Coulomb would feel if it were placed at that location. If instead you place half a Coulomb, you're going to feel half the force. Now folks, think about it in terms of a rate. If you went to a gas station and you asked them, how much is it going to cost to fill up my car? And they ask you, well, what kind of car you got? Well, I got a Toyota Camry. So is the gas tank full or empty? Oh, it's about half empty. Oh, and they look up in these tables and they, oh, that's going to cost you $33. That's going to be slow. Instead, they just say, hey, a gallon costs $3, except now it costs $2. Okay? And if you need 15 gallons, do the math. It's $2 for each gallon. You need 15, it's $30. Same thing with the electric field. If I had 1 Coulomb, it'd feel 5 newtons of force. If I have 2 coulombs, it'd feel twice that force. I never have 2 coulombs. Typically what I have is a micro Coulomb. That's going to be 10 to the minus 6 coulombs, or a nano Coulomb. That's going to be 10 to the minus 9 coulombs. So what if I have 1, let's say the electric field right here is 5 newtons for each Coulomb. What if I put 1 micro Coulomb there? I'm going to get 5 micronewtons of force. I just scale it. Okay? Now again, I left the units off. First of all, note, the Q in this equation does not create the electric field. The Q in this equation is the charge that experiences the electric field. It's the Captain Kirk that gets pushed.
Wouldn't that Q generate its own electric field, or would those two interact at all?
Yes. That Q is going to make its own electric field, and I would use that electric field to find the force on the other charges. But when I'm looking for the force on this charge, it doesn't push on itself. And so I look at the electric field due to all the other
So its field
charges.
doesn't modify the other field at all?
Only if it moves the other charges. Only if it moves the other charges. Okay. Now, the units, we've already talked about this, but let's just review. If the force is in newtons and the charge is in coulombs, then the electric field has to be in newtons per coulomb, and we're going to pronounce it newtons for each coulomb, for each 1 coulomb. Okay? Now, I've got some examples. I've got a set of examples we're going to go through to try to make this make sense. At the location marked with an X, the electric field is 2,000 newtons for each coulomb, and it points to the right. So it points to the right. What is the electric force, size and direction, on a 6 microcoulomb charge placed at the x? So I place that 6 microcoulombs there. It's positive 6 microcoulombs. What direction is the force going to act? What direction will the red vector point? In the same direction or the opposite direction?
Same.
In the same. If a +1 coulomb is going to be pushed that way, a +6 microcoulombs is just other. It's just going to be pushed to the right. Okay? Now, if I plug in those numbers, I get a value of 1.2 times 10 to the minus 2 newtons to the right. Now, folks, these values up here in this example are typical values you would find in a laboratory. And yet my experience has been that when we use numbers like this, it becomes mathematics. It just becomes a bunch of symbols on the page. So let me revisit this example with numbers we can wrap our head around. What if the field is only 20 newtons for each coulomb? And what if instead of 6 microcoulombs, I actually have 3 coulombs? I mean, we've destroyed Bozeman, but for the sake of understanding, let's make it 3. If this field is pushing with a force of 20 newtons on each coulomb, and I have 3 coulombs, what's the total push? 60. That's all it is. That's all it is. How much are you going to pay for your tank of gas? Okay? That 20 is the rate. $20 per gallon. That's in Europe. Okay? And I want 3 gallons. Well, that would be 3 liters. Oh, we got that. Now, what if that charge that I put there were the same size, but it was negative? What if it was negative 3 coulombs? Now, this is where some people, when they're beginning their study, struggle. If I look at this formula for the electric force, I have to remember that it's a vector formula. And if I have a vector pointing this way, let's call that vector C, and I multiply that vector by 2, well, that just makes the vector longer. I can multiply that vector by any positive number, and it'll stay pointing the same direction. It's only when I multiply it by minus 2 that I can change the direction. Now here's how this works. If that charge is minus 3 coulombs, and if that electric field is 20 newtons for each coulomb to the right, then that's going to give me 60 newtons. The coulombs cancel, and the minus sign goes with the right to give me negative right. What's negative right? Left. 2 rights don't make a wrong, but 3 lefts make a right. Just saying. Okay. So whenever you have a negative test charge, that's what we call that little charge that I put there, test charge, the force in the electric field will always point in the opposite direction. Okay? Now, what if I put it somewhere? What if I put it somewhere else? What if I put that test charge over here? I don't know. It turns out the gravitational field is boring. It's the same everywhere in this room. But an electric field can change drastically from point to point. And that's why we call this little guy a test charge. Because typically what we do is we take a little charge and we move it around the room and we see how it's getting pushed. And that, plus this equation, tells me what the electric field is everywhere in the room. Okay? So my answer here is who knows? I have to be at the x where the E is given. Second example. A charge of -5 times 10 to the minus 8, we could also call that -50 nanocoulombs, feels a force of 0.2 newtons to the right. Now it's a negative test charge, so the electric field at that location is going to point which way?
Right.
To the left. Okay? And to find the size, we would use this formula in reverse, solving for E, and we would get this value here. Now again, if I did that mathematically, I would say these are vectors. The force was 0.2 newtons to the right. This is a -5 times 10 to the minus 8 coulombs. And I want the electric field. The electric field is going to be 0.2 newtons over 5 times 10 to the minus 8 coulombs. I put the minus sign, this becomes right over the minus sign. Well, that's like dividing by -1. That's the same as minus right, which is the same as left. Okay? Now again, these numbers are realistic for the lab, but not helpful to us. What if we made that -5 coulombs and the force was 15 newtons? Well, if I had to split up those 15 newtons amongst those 5 coulombs, each coulomb is going to get a push of 15 over 5, or 3 newtons for each coulomb. 3 newtons for each coulomb. That's all it is. It's just like a rate, just like the price of gasoline. Okay? That's what we mean by electric field. Now, where does E come from? We look at this formula. The force that we're calculating is the force on this charge here. The charge that we call the test charge. Okay? The one that's actually feeling or experiencing the force. The electric field is created by all the other charges in the universe except for that one charge that we're looking at the push on. Now, it turns out because of that 1 over r squared dependency, where twice as far away is 1/4 as strong, 3 times as far away as 1/9 as strong, you don't really have to worry about all the charges in the universe. You don't even really have to worry about the charges down the hall. Just the ones close by. But this charge doesn't push on himself. This charge is the one that's being pushed. This is the Captain Kirk that's being thrown on his keister. This invisible electric field is created by the other charges, the not Captain Kirks, the Klingons, if you will. And there is no force until you put the charge there, until you put Captain Kirk in the field. Is it all coming together? Beam me up, Scotty. Okay. Now, let's get the direction down. If I have a positive source, a positive Klingon, if you will, that source is going to create an electric field over here. And that field is going to point what direction? Or do we? Remember, the electric field is the one with the waffle words. The electric field says, if I reach into my pocket, and if I pull out +1 Coulomb, and if I put it at the X, the electric field will just be how hard that 1 Coulomb is pushed. Now, if that's positive, and this is positive, which direction is that +1 Coulomb going to be pushed? Away. Away. And so I'm going to get an electric field away from a positive. Now, if I've got a negative source, a negative Klingon, again, the electric field is the force that would act if I pulled out a +1 Coulomb and put it there. Well, a +1 Coulomb would be attracted to that, so the field at that location would be towards a negative. And it's always going to be away from a positive and towards a negative. Now, folks, I'm going to pause right here and just tell you a little bit of history. Initially, this idea of an electric field was a gimmick. The fact that this charge here could push or pull on a charge back there through empty space was offensive to a lot of scientists. They understood how you could exert a force by pushing on something, but this thing here, pushing and pulling on that thing clear back there, that's too much like witchcraft and someone needs to be drowned. Okay? So, what they did instead is they did a two-step. Okay? They said that this charge, the source charge, changed the room. Its existence in this room changes the room. Sets up a field that you can't see everywhere in the room. And then the second step of the two-step, the field pushes back there. So I didn't have to deal with this action at a distance because, hey, the field was back there and it pushed. Now it turns out that even though this thing started as a gimmick, as a convenience, we found out it was real. When you look at what radio waves are or television waves or light, they're all electromagnetic radiation. And we find that electromagnetic radiation is an honest-to-goodness electric field changing and creating a magnetic field, which changes and makes an electric field, and it just bootstraps itself across the empty space. It turns out we just made it up as a mathematical trick, and it turned out to be real. Who knew? Okay, that's not going to be on the test. The question is, how big is this field? We know what direction it points, but how big? Well, that's given by this formula. And notice I'm calling that Coulomb's law. Well, that's strange, because on a previous slide I called this Coulomb's law. I said the electric force was equal to K Q1 Q2 over R squared. Well, we just said that the electric field was defined by this formula. The electric force on this test charge was given by the electric field at the location of the test charge times the test charge. Now, if the electric field has a magnitude of K Q source over R squared, and I plug that up into here, what I get is that the electric force has a magnitude of, there's a K, there's a Q test, there's a Q source over R squared. Which is exactly what I had here, where Q1 is Q test and Q2 is Q source. Here, I'm talking about an action at a distance. The two are pushing on each other. Here I've broken it up into a two-step. The source creates an electric field. The electric field pushes on the test charge. It turns out that this is the better way to think of this interaction, because we're going to find that there's different ways to create an electric field than by just having a point source. We can have a sheet of charge, we can have a bunch of sheets of charge, and so this will be the fundamental equation right here. Okay? Check that your neighbor's on the bus. Okay. That constant, 9 times 10 to the 9, will be on the front page of the exam. It's called Coulomb's constant. Now let's look at the last example. I have a 2.5 microcoulomb charge. It's placed right there. And we want to find the electric field at a point 5 centimeters to the right. Now folks, what direction is that field going to point? To the right. Okay? Now, if I plug into my formula for the electric field, there's my K value, my Coulomb's constant. There's the charge that's creating the field. There's the 5 centimeters. I've got to put it in meters and square it. And what I get is a positive 9 million newtons for each Coulomb. Now, what does that plus sign mean? To the right. However, if I had put the X over here, I might have put a minus 5 centimeters in here, but it's getting squared. I would still end up with a plus 9 million newtons for each Coulomb. So I ask again, what does the plus mean? Away. Because over here, the electric field is going to be to the left. The plus sign just means away. And indeed, if we put too much stock in this plus and minus sign with three-dimensional problems, we run into trouble. Because in 3 dimensions, I have an infinite number of directions. If I call one direction the negative direction, what do I name the infinity minus 1 directions that are left? They can't all be the positive direction. So what we do instead is when we use Coulomb's law, we use it to find the magnitude, the strength of the electric field. How big is it? Always a positive number. Always, 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 always. We never put in the sign of the charge into this formula because we're only looking for the strength. And then we use the fact that this electric field is away from a positive source and towards a negative source. Always away from a positive, always towards a negative. Okay, questions on that? Okay, I want you to look at problem 7 in chapter 16. Problem 7 is just like the 3 problems that you've been assigned for Wednesday. By doing that quickly on the board, I'm going to do your homework for you. Now,
Greg, you're both in -9.
I'm sorry?
Times 10 to the -9.
Oh, times 10 to the -9, thank you. So those would be nanojoules. Thank you. May I borrow your book? Okay, listen carefully to the wording here. It's incredibly important that you be able to figure out who is Captain Kirk and who is the Klingon. Who is creating the field and who is experiencing the field. With the spheres held 0.23 meters apart, what electric field, strength and direction, is experienced by sphere A? So, which one is creating the field and which one is experiencing the field? When I set up the electric field equation, which of these 2 charges do I put in there? The problem statement said that A is the one that's experiencing the field, that means Q must be creating the field, and because Q is positive, the field is going to be that way there. Okay? And so I would put in a K value of 9 times 10 to the 9th. I would put in QB as my source, 7 times 10 to the minus 9, and this distance is 0.23 meters, so I'd put 0.23 meters squared. And that would be the electric field. We've run out of time. Have a good weekend. We'll see you on Wednesday.